a shell cantilever beam, if you will, with a slight angle. So we're going to go ahead and create a part. It's going to be a 3D shell, and it's going to be extrusion. And we're going to keep the 200 millimeters. I believe the units in the millimeter, although the benchmark doesn't say anything, it gives you some generic numbers. You can look at the benchmark, by the way, under the help file, under Abaqus if you want. Go under search and browse guide, and somewhere there there's Abaqus, the benchmark guide. And there's a boatload of benchmark guides. One of them, the one that I'm mostly interested in, is the NAFEMS benchmarks. And you notice there are all these benchmarks available to you. Do you see that last one? Geometric nonlinear test. The test that we're going to undertake, at least we can do here, is this guy. Elastic large deflection of a Z-shape cantilever beam. With one caveat. You notice the orientation of that Z-shape thing? It's not exactly lining up with the global coordinate system. So that's what we're going to undertake here, and you're going to help me. So I'm going to draw the benchmark representation, which is going to look something like this. So we're going to dimension this one to be equal to 60. This one horizontal dimension, but let's start with this guy, make that 60. And then pick that, and then pick this point. So this one, there we go. We're going to make that equal to 60 as well. And then the vertical dimension between the two, I think, is equal to 30. The depth of extrusion is equal to 20, I believe. So did you get that? 60, 60, 60, and then I made the height equal to 30. And 30, I think, is the depth of extrusion, and that's the plate. What else do I want to do here? Let's create the material. The material in this case is, I'm not going to name them anything because these are the benchmark material. I have to be careful giving you the value of 2.05 e to the 5. Can you tell me what that pertains to? You'll get a prize. It's 205, 1,000, right? Which is exactly very close to that. Yeah. So that's the benchmark value that they use. The section, we create a section which is made of a shell, and that has a specific value of 1.7. I assume that would be in the millimeters as well. Everything else is. Now we're going to create an assembly. Okay, thank you. We assign the section, then we create an assembly. I'm anxious to create the assembly. Okay, so what I want to do now, what do you think I'm going to do next? I'm going to rotate this thing. About what axis?
Y.
Very good. About y-axis. So I'm going to say the first point is 0, 0, 0. The second point is going to be 0, 1, 0, right? That gives me the indication of the y-axis. And I'm going to rotate that not 90 degrees. I believe it was 45 degrees. Maybe not. How about minus 45 degrees? He took the word out of my mouth. Very good. There we go. However, my boundary conditions are going to be applied with respect to what? Global coordinate system. My part, or the assembly on which I'm going to create the FE mesh, is slightly rotated. I'm going to show you the results, and what I want you to pay attention is how we actually look at the results. Are slightly different form than what you used to. Okay, so I'm going to go ahead and create a step. I've done everything, creating part, material, section, assign the section, create assembly.
Okay. Oh. Sorry.
I didn't do okay?
I believe you
I thought I did. It seems to be rotated. Thank you for reminding me. A step. It's going to be general static. I'm not going to introduce material nonlinearity, so this is going to be the nonlinear geometric analysis that I'm going to undertake. Now I'm going to turn the flag that is called the nonlinear geometry on. Okay. Time period is going to remain 1. Again, time in this case is just a way for you to increment the load. The load incrementation, I'm going to start with a, it doesn't say anything in the benchmark value, so I'm going to give you some values. How about 0.01 to begin with? And what should we do with the last one? You're not helping me. Maybe 0.5, just see what happens. I'm going to change the maximum number of increments to 200, just to make sure that it gives me enough incrementation to solve the problem. And that is typically how you start. In the geometric nonlinear analysis, especially when you get close to the buckling, in this case we may not reach there, although we may, you really want to start with a fine increment of load. So you have to give it enough leeway. Notice the minimum number of increments, 1 times 10 to the minus 5. There are instances that you have to manipulate that as well. That is, the buckling is so critical so far as the transitioning is concerned that you may go to a number such as 1 times 10 to the minus 8 or 9.
Would you need to do like 2 steps, or could you?
You can do multiple step analysis, but good luck trying to figure out where that step is that you need to stop. So we're going to keep everything else intact. I'm going to go ahead, since I'm not doing plasticity analysis, I don't want to unnecessarily write a whole bunch of information. So I'm going to uncheck the strain and contact again, as if I'm doing linear static analysis.
Excuse me, I think that you didn't hit OK and the rotation didn't happen.
He still insists I didn't hit OK on the...
Same, the way I see it.
Okay, so let's go back to the assembly. Nobody else is saying anything. Why not, guys? So let's go ahead and rotate that one more time. Done. 0 and 0, 1, 0. We decided it was minus 45 degrees. Do you like that better? He is the one that is checking my work. As long as he's happy, I'm happy. So we're going to apply loads. Now, you are a lot of times avoiding concentrated force as much as possible. Unfortunately, in Abaqus, for you to plot, and this is going to be the big thing we're going to do here, plot load as a function of deflection. Remember, that's how we want to determine the critical load. For you to plot load versus deflection, you must have identified load at a certain point. At a certain point means that you have to have what? A concentrated load. So be it. That's what the benchmark is based on. So we're going to concentrate Y force at the 2 nodes up here. And the benchmark value for the CF2, I believe, is 104.5. What else do I want to do here? Turn on the flag that is called follow nodal rotation. Remember, now this is geometric nonlinear. It can really deform tremendously. I don't want my load to be remaining in the vertical orientation all the time. No, I want it to be upward. So let's just go ahead and remove that minus. For some reason I thought y direction was negative. Yeah. Now you know what the benchmark is going to do. Something that already has a tendency to move up, we're going to move it way up beyond its limit, so to speak. The boundary condition is a simple global constraint in all degrees of freedom. So we're going to go ahead and pick symmetry, anti-symmetry, and castray, and pick that edge, cantilever it pretty much, and we're good to go. Switch to the mesh. And let's go ahead and pick the mesh of unreduced integration, meaning full integration. It should be shell. We're also going to do a quad structured mesh. And let's pick a reasonable mesh size, although again the benchmark gives you specific values for the mesh, which apparently with Abaqus's robust element definition doesn't make a whole lot of difference. Although this one is going to be a big mesh. So let me try that one more time. Let's give it a value of 5. 222 elements. Is that okay? We should be able to run that reasonably expediently, so we're good. We're going to save that. I always tell you I'm going to change that directory and I fail.
Dr. C, is there a reason why you always save right before you submit the job?
Yes.
What is the reason behind that?
I've been stung by the failure of Abaqus too many times, at least in the older version. Just when I'm making a sophisticated run, it exits with blue screen of death. Yeah, it's just a habit that has remained with me. I remember one time I ran a problem, and it was supposed to take a number of hours, and it was really complex. As soon as I started to run, it bombed, and all my work was lost. So I had to create the whole model all over again. Now you know why. So I won't repeat that mistake again.
Why you did not use that with symmetry?
Because it's the benchmark problem. And notice the boundary condition is offset from the global Cartesian coordinate system. So Z-shaped benchmark. All right, so we're going to go ahead and create a job. That's the solution of Z-shaped benchmark, right? Just for good measure, I'm going to save that one more time. And now I'm going to run it. And I'm going to activate the monitor. Just keep track of things. Enlarge that so we can see warnings. Okay, very good. I inadvertently checked the strain again, and it says strain is not available. Do you see a 1U appearing up here? Is it no, it doesn't mean it's not good. In this case, it is kind of an indication for you that maybe at that instant, what has happened? Your increment of load has exceeded what was supposed to give you the convergence of the solution. in a layman's term, that would be possibly indication that you reached some instability concept. More importantly, pay close attention to the equilibrium iterations that it has taken for each one of these increments of load. Started with 2 and then 3, 6, 7, 7 iterations, and it says, oops, too much load. And you notice the increment of load before that was 0.05, then it went to 0.076, it bombed, it went back down to 0.019, and it kept it kind of reasonably low increments of load all the way to the end. All right? So you naturally, the first thing you want to do is go look at the results. But the first thing I want to do is go to proper orientation, go to the first step. That is the left arrow. And instead of one mesostress, I want to look at the displacement. And the displacement I want to look at, I requested too many outputs. I'm going to be U2, meaning the y direction displacement. Watch as I'm incrementing the load. These are not unified and the uniform increments. This is whatever that Abaqus decided to use as the increment. Okay, so you see what is going on now. That's why they call it a benchmark. So now I'm up to 93 millimeters, 97, 100 millimeters in the y direction. Is that nonlinear enough for you? So there you go. That's the shape of my problem after I've applied the complete load to the system. So how would I tell somebody that I have achieved a nonlinear solution of some kind? Let me go back to the undeformed contour shape. And let's just create generic plots in this case to see what we can come up with. And that would be kind of a stopping point for us after I'm done. So let's go ahead and create XY data. You have the first two options can come in handy sometimes. I'm going to start with the ODB history output. Notice the history output. You got a boatload of stuff available to you. Two things that come to mind would be a strain energy plot, or you can say total energy plot. And then here's what I want you to always keep an eye on. There is a concept called artificial strain energy. That artificial strain energy is the measure of error that you're encountering from equilibrium. The higher the artificial strain energy, the more inaccurate the model is going to be. Now, if you plot that by itself, you're going to get scared. So I'm going to just pick artificial strain energy and say plot. You see what happens? You're going to say, whoa, bad things are happening. No, look at the unit that you have here on the vertical axis. 1.2. Let's say 1.5 is the maximum. What is the unit of that? What is the unit of that? Energy. Remember what we're applying the load in? Newtons and millimeters. You apply the load by the displacement in the SI unit, you get the energy unit, right? The work unit. Newton millimeters is what you got. Now, I want to superimpose on this. To superimpose a plot, make sure you hold the shift key, and I'm going to go ahead and go down below and say total energy. Oh, no, not that one. That's a bad one. Not the shift. Control, excuse me. Shift plots all of those things for you. You don't want to do that. I'm going to do the total energy and plot both of those. Now, there's negative value here, and then it goes toward what? The positive value. This is a very interesting point. but the Abaqus is not giving you much information. I'm going to switch to strain energy versus artificial strain energy, and then plot these two guys. Well, you can barely see anything. Let me replot that again. You can see the orange color right on the horizontal axis. You see the pinkish or reddish color going up. This is your strain energy. Down below is your artificial strain energy. That is deviation from your actual strain energy. Not very much. Do you see the unit now? No, you don't. So let me dismiss this thing and double click on my plot and change the font size if I could. The axes, font 12. That's for my y-axis. Do the same thing for the x-axis as well. What about the title? Change the title font as well. Oh, that's big enough already. Okay, so notice the unit. Something times 10 to the power of 3 is your strain energy. So from the standpoint of the comparison of your artificial strain energy, which is down here, versus the actual strain energy, you don't have much to worry about. What you want to look at is the behavior of the strain energy. It's a nonlinear behavior, so your expectation is that the problem is going to indeed behave in the nonlinear form. So I'm going to go back and plot this thing, contours on undeformed shape again. Any questions on this plot? How I manipulated the plot. We'll come back to plot in a little bit more. So now I want to go back and plot not the history output, but the particular parameter that we're interested in. That would be ODB field output. You'll get this dialog box that says, what do you want to plot? Integration point is the default. That's where you want to plot stresses, etc. I do, however, want to go to the unique nodal, so I can plot the displacement at the node. And on that, I can plot, let's go way down below here, and do a spatial displacement. Open it up. I don't want to plot the whole thing. I want to plot just the U2 variety of it. And now I want to say plot. At least one entity should be selected. I didn't tell it what is it that to plot, what location, right? I simply said plot U2. Now you click on the tab that is called Element and Nodes. Notice the prompt says in that window, click Edit Selection to pick in viewport. You need to do this. You need to click Edit Selection. It's not joking. Edit Selection, zoom in and say, what point do I need to pick? I want to highlight the selection on the viewport and maybe the middle point, right? Or you can pick one of these endpoints. It doesn't really matter. I'm going to pick the endpoint. I have ulterior motives here. This is the endpoint that I picked, and I'm going to say plot. So this is a variation of the displacement along the y-axis in the millimeters, of course, as a function of what? Can you say what that time stands for? Very good. Increments. Don't say loads. It's not load. It's just the increment that it has taken. You can also do the following. You can also say, you know what? Instead of the plot that I just did, I want to plot the actual load as well. So I'm going to uncheck spatial displacement and instead go and look for, what is it? Point loads. Do you see the point load? CF point loads. I want to do CF2, right? That's where applying the load as a point load is going to come in handy. And I'm going to say, all right, pick element nodes again. That same node that I have picked, and I'm going to do plot. So this is a load as a function of increments again, or time step, if you will. Do you see some interesting phenomenon here? Your load is not being applied or varying linearly, a clear nonlinear. You're going to say, well, it would be really fantastic if I can plot load as a function of displacement. No luxury exists in this case. But there is a way to manipulate the plots. And help me out here. So I'm going to save this thing. Using default names, we'll say OK. I'm going to go ahead and do that one more time because the previous one, I don't know if I saved it or not. I'm going to uncheck the load and go back to my spatial displacement, pick the U2. I think elements in node has been selected. We're going to say plot, and I'm going to save that as well. So I've saved 2 plots, right? I'm going to dismiss out of here. Go to manage XY data. So there are 2 of them that I have plotted. I really don't need this one. I'm going to say the second one delete. So the first one, you see what a nice name it has been given. This says CF, CF2, PI, all that crazy stuff. I'm going to just rename it and say what? Applied load. How's that for a name? And the other one, I want to rename that as what? Very good. Y displacement. Okay. I'm going to dismiss this thing. So now I'm going to the manage XY data, or maybe I should say create XY data. At this point, I have 2 plots that I've created. I'm going to now operate on XY data. So remember the step. Operate on XY data, continue. Now you're given a nice description, lots of functions you can operate on. You see the functions on this side? All kinds of stuff available to you. I'm sure you're looking forward to the Butterworth filter variation of it. But no, we're not going to go into that, not even sine hyperbolic, etc. Instead, I want to combine the 2 plots. It says combine capital X comma capital X. All right. So notice what it says. I want to give it a first variable name, which is going to be, let's try with the Y displacement. Double click on that term, and then enter comma, that is type the comma yourself, then double click on your other axis. So both of them are going to have what? Load as a function of increment. The other one is the displacement as a function of increment. By doing what I've done, it's removing the increment, is going to plot one as a function of the other, load as a function of displacement, or displacement as a function of load. So I'm going to now simply say plot the expression. Do you see what has happened now? I have force as a function of the displacement as my plot. And you can save this expression in case you want to keep it for posterity. Now, here's where the Abaqus's Fortran heritage comes in handy. Don't type spaces or characters. It'll balk at you. So just load versus displacement. Dyslexic version of it, of course. There. So I've plotted load versus displacement, and you're going to say, well, you know what? The plot that you have, I'm not really all that happy about, the features I have. I'd like to plot it myself. Where should I plot it? I'm going to go ahead and manage XY data, load versus displacement, and I'm going to say edit. This is the data that you're plotting. Right? So you can do that kind of stuff. Copy and paste it to your Excel if you want and plot it as if Excel is really a wonderful plotting software. But if you have more of a scientific plotting scheme, that would be the preferred form. Okay. So from your first force versus displacement plot, what can you tell me? I said all these things to you and you're not saying anything to me? I have a critical load. Wow. Okay, great. Where is it? Right over here, right? So you should be able to tools, if I'm not mistaken, there's a query. Probe values. You see as I'm moving around? I don't know if you can or not. See that? The cursor up above as I'm moving around here. It gives me the value of X and Y in this case. So this is my point of instability of the structure. That's probably where you saw that 1U appearing because the slope became equal to 0, increment was applied, and it says, oops, I'm not getting to the solution, so I'm backing up from there. Now, what did you say the behavior was? Somebody here said snap through? Maybe. The reason I said the maybe is because I don't have enough load post-buckling to get a very clear picture. But you're right, it is beginning to show the shape of a snap through. On the other hand, it could very well come back and go back up. So that's the point of instability. This is the maximum number of increments that I've applied in this case. This is just pure geometric nonlinear analysis. A lot of times in the geometric nonlinearity, load incrementation may not give you a good way of solving the problem. In other words, load incrementation may lead to solution instability. A lot of times in the geometric nonlinearity, especially in the post-buckling phenomenon, here I'm just barely beyond the buckling, but post-buckling means that I'm going to buckle and then I'm going to snap back or snap through and go through another regime of stiffening of the structure. In that sense, the displacement incrementation is a more robust way of solving the problem, meaning instead of load controlling the solution so far as the increment of load, we have the displacement control, meaning you're translating that into how I want the structure to deform and break that into a number of increments.